the kind of importance the materials have. And all around us, we see materials. And in fact, even ages people have defined in terms of materials. People started calling Stone Age, the Gold Age, and the Copper Age, and the Bronze Age, Iron Age. You name it. Now people talk it as Silicon Age and Nano Age. So everything revolves around materials to a large extent. And the quest to work on materials has been there for ages. I can go back to almost 10,000 BC, if you are able to see the slide, and where mostly people used stones. Okay, so that's what, nothing but ceramics and glasses, for example. People also used the wood, which is nothing but a composite. uh, and polymer, I would say. So variety of polymers. And the only known metal those days was possibly gold. Okay. And then slowly you have metals started coming into picture. So if this particular curve tells you the relative importance of various materials. So if you look at around 1950s, when the Second World War was going on, and people were more interested to develop things which are warheads, which are aircrafts and things like that. So metals started taking a lot of importance. So that is the reason why you see a lot of importance coming to metals in that age period of 40 to 60 or so. Then slowly again, if you look at as of today, around 2020 or so, more or less they are all occupying a similar proportion: metals, then polymers, then composites, and ceramics. So just to tell you that variety of materials are being used for variety of applications. But the quest of mankind to peep into materials has been there for a very, very long time. They wanted to understand why the materials behave the way they behave. And the first such microscope came, for your information, by Robert Hooke. Many of us know about Hooke's law. So it is Robert Hooke who talked about it. In fact, even before him, I would say, the person who made the first microscope is the person who made the first telescope. Okay, Galileo, for your information, is the one who made this so-called compound lens microscope. Let me just look at pointer. Yeah. So this is, I can say, possibly the first microscope ever made. And then now people are talking about not just 2D microscopy, but not only 3D microscopy, a 4D microscopy. Okay. People are going beyond understanding 3D microscopy. They are talking about what is called 4D microscopy. That means what happens to something with time. Okay, for example, I want a reaction to be observed under a microscope as a function of time, how it is happening. For example, I have a catalysis reaction happening on a surface. I want to know how this catalysis reaction is happening, what kind of phases are forming during the catalysis as a function of time. So time is being added as a fourth dimension, and people are interested to know about 4D microscopy. Quite a number of what we call them as in situ microscopes have come now. Where I have a microscope, and inside the microscope I can either do a tensile test, I can take a sample, pull it, and see what happens to the material when I pull it. I can also take, for example, long back, my first visit abroad, 1996, I went to Germany, where I was working on nanomaterials. I wanted to know how the nanomaterials grow when I heat them. So I heat the sample inside the TEM, transmission electron microscope, and see how the nanoparticles grow, and find out what is the rate at which they grow. So in front of my eyes, I can see them growing. So all these in situ things, people have been doing it, and variety of microscopes are being developed where such kind of in situ experiments can be done. But all this is basically to see whether we can make materials better than what we already have. Long back in 1900s, almost more than about early 2000th century, I would say, people wanted to make lighter and stronger alloys. Okay, there was a gentleman by name Wilm who was trying to make an aluminum alloy which is as strong as the steel. By the time people know that if I take a steel and quench it from high temperature to room temperature, it becomes suddenly strong. Okay, and we all know that there is some kind of a phase transformation happens, that there is something called martensite that comes out of it. That is something people knew, that steel becomes stronger when I quench it from high temperature. So this gentleman kept on doing that experiment, taking an aluminum copper alloy, kept on quenching it from higher temperature to know whether it will become stronger. And unfortunately, that alloy has never become stronger by quenching. Over a weekend, he left that sample and comes back on Monday and looks at that particular sample, again measures the hardness. He suddenly found that the alloy has become very strong. Over the weekend, it has suddenly, as if an angel has come and made it very strong. And he did not know why it has become strong. But as a good scientist, he kept on repeating this experiment. That means quenching the aluminum copper alloy from a high temperature and holding it for 1 or 2 days. And at the end of 2 days, he started seeing that the alloy is becoming strong. This they started calling it as age hardening. We all become softer by age. Typically, as I always say, the grandparents are softer than the parents, typically. So whereas here, by aging, something is becoming harder. Immediately, a company called Dural has patented this, and they started calling it as duraluminum. All our aircraft's bodies are made of duraluminum now. You are all aware of it. And Wright brothers have used it in their first flight in 1903, this particular alloy. But at that point of time, nobody knew why this alloy was strong. Almost about 35 years later, people have developed a microscope. And in that microscope, when somebody has put this particular sample, they saw a wonderful nanoparticles, okay, which have an acicular kind of structure, nanoplatelets, if you can say so. And then people started understanding it is because of these nanoplatelets the whole alloy is stronger. And people started calling this as precipitation hardening. So the alloy actually, when you quench it, it is in a supersaturated condition. And if you leave it like that for some time, it starts precipitating certain extremely fine particles. And in an optical microscope, they were not able to see it. Those days, what was available was only optical microscope, and they could not see it, and they had to wait for 30 years. And 30 years, there is a great gentleman by name Ernst Ruska, okay, who came up with a new microscope called transmission electron microscope. This was the microscope that he was working on in 1932, and he had to wait almost 50 years. And an young gentleman like this has become an old gentleman when he got a Nobel Prize. And he got a Nobel Prize because people were excited about scanning tunneling microscope those days, early 80s, and people wanted to give a Nobel Prize to those people, Binning and Rohrer. And at that time, they realized that suddenly that there is a gentleman who actually came up with high resolution microscopes almost 50 years back. And luckily, he was alive. So he was also given a Nobel Prize at that time. So to tell you that sometimes people have to wait long for their innovations to be recognized by people. But this microscope has now changed the whole world, and people started looking at materials at a small scale in these microscopes. But before people had such microscopes in hand, people used to look at the way the materials shapes are and try to understand how the atoms are arranged inside. Everybody wants to know how the atoms are arranged in a material, and so that we can probe deeper into material. For example, on the left picture, if you see, these are what are called snowflakes. Even Kepler in 1600s worked a lot on them. And if you carefully observe, they have hexagonal structure. And that is from where people thought maybe ice has some hexagonal structure. Until XRD came into picture, X-ray diffraction came into picture, people did not know how to know the structure of a material. And after the XRD came into picture, people now know, yes, ice has a hexagonal crystal structure. You take sodium chloride crystals, they are all cubic in nature. But the fact that they have cubic crystal structure came to be known only after XRD was known. So people used to look at materials and then guess what could be the internal atomic arrangement from the external morphology of a material. And this is how people used to do. And then people started dividing materials into two groups. One they call it as crystalline materials, another they call it as amorphous materials. And crystalline materials are those where you have a three-dimensional periodicity along with a local rotational symmetry. So they said a material to be called as crystalline should have both rotational symmetry and translational symmetry. And such a crystalline material, if you subject it to an X-ray diffraction, you get peaks like this. And by looking at the peaks, we can find out the crystal structure to some extent. Some calculations have to be done, but one can do this. And if you put the same material in an electron microscope, you get spots like this, white spots. And by looking at the way the spots are arranged, the rangoli kind of a pattern that you have, and by analyzing the rangoli, you can understand what is the crystal structure. But the moment a material is amorphous, uh, uh, like a glass, for example, we all know, and these glasses, the window glasses, for example, if you put a window glass in an XRD machine, you get a broad peak like this. This tells you that there is a random scattering happening, but because there are no clear crystallographic planes, atomic planes, you get a broad peak. And if you do the same thing with a transmission electron microscope, you get a very, what is called diffused ring. And the moment you see a diffused ring in a TEM, and the moment you see a broad peak in a XRD, you clearly say, oh, this material is amorphous. But then there are things in the world, in the nature, which are interesting, which have very, very interesting shapes. For example, flowers. Many flowers we know, they all have pentagonal symmetry. And pentagonal symmetry, five-fold symmetry, is considered to be forbidden symmetry by crystallographers. They said such a symmetry cannot exist in a material because a five-fold symmetry, which is a rotational symmetry, cannot coexist with a translational symmetry. For example, if you want to fill your floor in your house, you cannot take pentagonal tiles and fill the whole space. You will have some voids left out. In crystallography, we call that as frustration. So people thought this is not possible in materials to have a three-dimensional packing to happen. But then people started seeing that there are materials where the grains have a pentagonal symmetry. This is a grain from an aluminum copper alloy, our aluminum copper iron alloy to be exact. And then this is another material which also shows grains which are growing like flowers, which are pentagonal flowers. And when somebody in 1982 by name Dan Shetman, he is from Israel, he was working in Caltech with a professor, and at that time when he saw a particular aluminum alloy, he was also excited about making an aluminum alloy stronger. He took an aluminum manganese alloy, he quenched it from liquid and got an alloy microstructure where there is a precipitate inside the microstructure. He was looking at the diffraction pattern coming from the precipitate in a TEM, and he saw, interestingly, a very nice five-fold symmetry. You can see so many pentagonal things here. This is a diffraction pattern. And he said, and the central spot has 10 spots around it. He put a question mark 10-fold in his notebook. And this is done in April 8th, 1982. And nobody believed him, okay, including his own guide by name John Kahn. John Kahn went to the extent to say, Dan, you are bringing disgrace to our group and talking about something called quasi-crystal, which nobody believes. Okay, nobody believed that something called quasi-crystals exist, because the crystallographers were very particular that crystal means it should have both a rotational symmetry and a translational symmetry. And he, 82, when he submitted this paper to Journal of Applied Physics, they immediately rejected it. Then he talked to two mathematicians, and these two mathematicians said, in principle, if a particular material has no periodic arrangement, but it has a quasi-periodic arrangement of molecules, for example, something like a Fibonacci sequence, then if you take a diffraction pattern from such a material, you can end up into a five-fold symmetry. This was proven, and a lot of people who work on tiles, Roger Penrose, for example, has done a lot of such work and demonstrated that five-fold symmetry is possible. Okay, and finally, after 2 years, this paper of him got appeared in Physical Review Letters. But what is more interesting is that in 1991, the International Crystallographic Society has now changed the definition of a crystal. So far they said a crystal is something which has both rotational symmetry and a translation symmetry. And now in 1991, they say a crystal is any solid having an essentially discrete diffraction pattern. As long as you get sharp peaks in a diffraction pattern, then immediately you can call it as a crystal. Okay, that is how quasi-crystals have become a subset of crystals now. Okay, and Professor Ranganathan, my own supervisor, started calling that this is the first time there is a divorce between order and periodicity. That material can have an order and it need not have a periodicity. Okay, and that's something that Dan Shetman has brought about. And in 2011, this gentleman was given a Nobel Prize. But what is more interesting is 1978, a paper was published by a few people from Banaras Hindu University. Another alloy, aluminum palladium alloy this time, again aluminum alloy, but not an aluminum manganese alloy, but aluminum palladium alloy. Again, if you look at the diffraction pattern of this particular precipitate, you see pentagons here. You see a tenfold symmetry here. But unfortunately, we did not get a Nobel Prize. Okay, the only reason is nobody again in India also believed. Their supervisor by name Professor Anant Raman, Professor T.A. Anant Raman, T.R. Anant Raman, very famous professor from Banaras, he said such a things do not exist. Then immediately, as usual, what happens in India, if your professor does not accept what you are doing, the student usually tends to drop it off. And they have kind of dropped it off and maintained a very low key. Whereas this gentleman, Dan Shetman, did not leave it. He went on finding out different aluminum alloys, different other materials, where he started proving that such a five-fold symmetry can exist, not in just one alloy, but in a number of alloys. And that's how he has become famous and a Nobel Prize has come. And if you see this, this is a pattern on the right bottom side, which is what we call it a high resolution electron microscope, which we use to see atomic resolution image of such a quasi-crystal. If you carefully see, you see a number of pentagons here. Okay, every dot is an atom here, and you can see how atoms are arranged in. There is no clear periodicity here. Okay, the distance between any two atoms in one particular line is not equal, but they have a symmetry there. Okay, a beautiful symmetry. And this is something which has made people very excited, and a lot of people have started working, and India also has contributed a lot in various types of quasi-crystals, and IIT Bangalore, Professor Ranganathan's group, Professor Kamanyo Chattopadhyay's group, even Banaras Hindu University, Professor P. Ramachandra's group, Professor Shastri's group, all of them have done exceedingly good work. Then the people started saying, can we still go deeper and see, atoms in a material? Okay, 1950s or so. Even though electron microscope came into picture, it was not easy to get such a high resolution, to see a resolution as small as 1 angstrom, for example. Okay, because we know interatomic distances are all about 1 angstrom or so. And the microscopes those days, which have even the best electron microscope, used to give you about 2 nanometer resolution. That means 20 angstroms resolution. Here we have now microscopes available. This is one thing called atomic force microscope. If you take your hand and put it under AFM and start seeing, as you keep on magnifying, you start seeing the blood cells. Okay, you come to much higher resolution or a much higher magnifications, you start seeing the DNA. You see the helical structure of the DNA. You even see the molecules in the DNA. All these are possible now. And people are going to the extent to say you can see atoms. Okay, this particular microscope, which we call it as Titan, it costed us about 20 crores at IIT Madras when we bought it. And this can show the dumbbell structure of atomic arrangement in silicon. Okay, silicon has a very famous dumbbell structure. Okay, so each dot is an atom. And this particular microscope can give you a resolution of 0.7 angstroms. One of the best resolutions that one can ever imagine in a material. Such kind of things are possible now. People are able to see these atomic arrangements. For example, this is a material, again an aluminum, where you have an amorphous pocket inside a crystalline material. Here you see all dots which are periodically arranged outside this, kind of a elongated sphere, and inside this region you see dots are there, but then they are all randomly arranged. So that means you have an amorphous pocket inside a crystalline material. This is only a 2D imagination of a material. But now people are talking about, can I see atoms in 3D? So you have microscopes available where you can see, for example, this particular image is one such a 3D image. I will show you a few 3D images where you can see atoms in a material. I have a, let's say, steel. I have iron and carbon in the steel. I want to know where is carbon going and sitting. And it is possible now to see such things. And people are all using such an exciting microscope to develop materials which are newer materials, to design newer materials so that we can come up with exciting new materials. But this particular whole thing has been mostly driven by what people call it as nanotechnology. Because nanotechnology, where particles are extremely small, so you want to use microscopes to see those fine particles, and they're all extremely small. And why people are excited about those small particles is the properties of materials significantly change when you decrease the particle size. For example, we all know gold is yellow in color. Okay, all of us are aware, and the girls here are excited about the glittering yellow color of gold. They all want to buy it and wear it. But the same gold, if you take it to 50 nanometer particle size, it becomes green in color. You take it to 25 nanometers, it becomes red in color. You make gold into 10 nanometer particles of gold, gold will be black in color. Okay, so gold can be black. And this is possible by simply changing the particle size, and which changes the optical properties. Why optical properties? Magnetic properties of materials, electronic properties of materials, mechanical properties of materials. Most of these properties keep changing as you decrease the particle size, and people call these as size effects now. Okay, and what you see here, on the both sides is basically some window glasses in old churches, where people used to use what are called emulsions. Okay, colloids they call them as, and people used to add. Even Faraday is known to have worked on such experiments where people use nanoparticles, nanoclusters in a glass, embed them into a glass, and you get different colors by simply changing the size. This is another example where the same silica, for example, if I am at Chennai, I go to Marina Beach, take the silica particles, make them nano, and change the particle size, and have different particle sizes, put them into simply water, and you can get different colors here, and depending on the size of the particles. Different sizes of particles give you different colors. So different optical properties can be seen. And Feynman went to the extent to say, can we really make things at a small scale? He wanted to say, can I write the whole Encyclopedia Britannica on a drawing board pin? And in fact, he said this in a lecture in 1959. Unfortunately, people did not have an equipment to do that at that particular point of time. But by 1990, people have been able to do this. What they do is they use a technique called dip and nanolithography. What you see here, every white letter on a blue background is all written by this kind of nanolithography technique, where the distance between these arrows is about 60 nanometers. That means each letter is of the order of 50 to 60 nanometers. That kind of letters, it is possible. But then how do I see it? I need a microscope to see it. It is like a miniaturized writing with a pen, very sharp pen. And I need to use some microscopes such as AFM to see them. And people have gone to the next level to say, can I arrange atoms the way I want? You all see here IBM written here. Every dot is an atom now in this. So people are able to lift atoms from somewhere and put atoms where they want. And this is exactly what Feynman said in 1959. He said, I'm not afraid to consider the final question as to whether ultimately in the near great future, we can arrange the atoms the way we want. And this is something published in 1990 in Nature, and people are able to do it, and many things people are able to do. And even in India, our ancient scientific heritage is so great that many of you, if you have gone to the Qutub Minar, you would have seen this Delhi iron pillar, which is called Rustless Wonder. Iron was first made in India. When I was a BTech student in REC Nagpur, I was told iron is made by Bessemer. But then much later I came to know that iron was first made in the borders of Andhra and Karnataka, and it was called Ukku. Okay, if there are some Telugu speaking people sitting here, they will know Ukku means steel. So people could not pronounce that word Ukku. They started using the word woods. So Europeans have started calling it as wood steel, and this steel became so popular. This particular iron pillar has one speciality, that it doesn't corrode, but the wood steel that people made is used as swords, and it was so strong that it can cut a helmet into two pieces. What is more beautiful is also that this particular steel has 1.2% carbon. We all know in metallurgy that 1.2% carbon steel is brittle. But how people were able to convert such a brittle steel into a sword by beating it. Any brittle material, you beat it, it breaks. That means people had the whole technology 2000 years back to be able to utilize such technology. What is more interesting is somebody took a piece of such a sword from a museum, put it into a microscope, which is called a high resolution microscope. Now people saw in them what are called carbon nanotubes or carbon nanowires, whichever you want to call it as. What is interesting is this was published in 2006 in Nature once again. And that is something which has excited people. How did people know whether they knew the technology of making these nano wires or nanotubes, or was it accidental? Nobody knows now because the whole technology has gone and people are struggling to replicate this kind of materials now. And such a technology existed in the country, such a great country ours was, and somehow 500 years of slavery that we went through, we all became kind of slaves now, that we always look towards somebody on the western side to tell us what to do, unfortunately what to do. So this particular nano has grown to such an extent that people have started using these nano materials for various products, cosmetics, toothpaste, you can say. I do not know what toothpaste you have used today. If you have used Colgate whitening toothpaste, you have already used nanoparticles. Okay, you have nanoparticles all around us. You have nanoparticles in fridge. People use to purify, to kind of remove bad odor in the fridge. People use nanoparticles in your aquaguard water cleaner to kill bacteria. So nanoparticles are there everywhere and are used in various applications, and also for super hydrophobic applications again, and textiles, for example, swimming suits, you name it, they are there. I'm starting from there to all kinds of technologies, whether it is your iPads, iPhones, or even laptops that we talk about. Everywhere, wherever miniaturization is happening, there is nanotechnology. You can see that. And many people, talk about how to make these nanomaterials. There are two particular ways. One is called a top-down approach. Another is called a bottom-up approach. Okay, the bottom-up approach is where you start from atoms and collect atoms, allow the atoms to come together and form a small cluster, and do not allow the cluster to grow. Okay, for example, PVD techniques, CVD techniques are some such techniques where you can make nanoparticles easily. And the other technique is what is called top down, where you take bigger particles and break them into smaller and smaller particles. And that can also give you, and for example, in our group, we have been using a technique called ball milling sometimes. We also use what is called rapid solidification. Take a liquid metal, liquid alloy, rapidly solidify that alloy, and you get extremely fine nanoparticles embedded in an alloy. For example, this is an aluminum alloy with about 94% aluminum and just about 6% alloying elements. You get a strength as high as 1400 megapascal. A normal aluminum alloy such as duraluminum cannot give you more than 400 megapascal. But now it is possible. It is not only possible to do that, we are also now able to get materials which can withstand their strength even at high temperatures. These are some aluminum alloys. We are now making what we call them as aluminum based super alloys. Okay, where an aluminum alloy retains its strength, 90% of its strength, almost up to about 400 degrees centigrade or 500, close to 500 degrees centigrade, which is very close to its melting point. Aluminum melts at 660 degrees centigrade. So even at 0.75 or zero point 0.8 of its melting point, its strength is almost 80% of its original strength at room temperature. All this is possible by embedding nanoparticles into aluminum. We also have done very interesting studies. This is again another nanotechnology for applications which are defense application. This is an application where people are making armor plates for these tankers. Whenever you use an armor plate, you have to weld these armor plates. Typically, people use steel. When you use steel, the weld joint is very poor. And as a result, if you fire a bullet, it pierces through it. Whereas if you take the same steel and do what is called thermomechanical processing, you can convert the microstructure into extremely fine microstructure. This is what is called nanostructure. We can make that nanostructure and we call it as nano steel, and it gives you such a high stress strain diagram where the toughness is very high. The area under the curve in a stress strain diagram indicates toughness. And once you make such an alloy, now you weld it. You see the welded joint is so tough that you fire a bullet, nothing happens. The base metal also is so tough that you fire a bullet, nothing happens. This is being now used by CVRDE at Azadi in Chennai. One can also make nanoparticles and use them as coatings. People are now talking about what are called self-cleaning coatings. We even did such coatings in even steel plants. For example, steel plants, you have huge ladles where the steel is poured, liquid metal at 1600 degrees centigrade, and the refractory bricks get worn out. We simply coated nanoparticles on the refractory bricks in Vizag steel plant, where the coating gives you almost 800 Vickers hardness, whereas uncoated material has less than 50 Vickers hardness. Okay, and you can see because of that, the wear resistance being so high, the life of the refractory bricks we were able to demonstrate can be doubled without much efforts. And just you need about 10 micron coating. That's it, nothing beyond that. And this kind of things can be done. And we also can talk about self-cleaning glasses. You can take a glass and coat nano titania, for example, and it gives you self-cleaning properties. Okay, and this is now become very popular. Quite a number of people are using it. We can also, as I was telling you, use ball mills like this, where you put balls and powder, and you can break this powder into extremely small particles, such that you get nanoparticles. You can see all of them. This is a scale which says 100 nanometers, this cell length. So each particle is about 20-30 nanometers. So we can make that kind of nanoparticles in variety of materials, whether it is ceramics, whether it is metals, whether it is compounds. Even in polymers also people are able to make such nanostructures, and people are trying to do. And what happens when you do that kind of a thing? The material shows enormously enhanced properties, exceptional properties. Here is an aluminum alloy where the hardness can go to 12 gigapascal, 12,000 megapascal, which means a yield strength of 5,000 megapascal, which means 5 gigapascal. 5 gigapascal yield strength is like a dream for any metallurgist, for an aluminum alloy. And that means it is much stronger than steel in terms of it, what is called specific strength. When you take strength divided by the density, you will know that this material, for a very lightweight, it gives you very high strength. And this is possible. And people also started seeing that this kind of nanotechnology has much significant advantages in various ways. For example, I can take these nanoparticles and sinter them at very low temperatures. Many of you know tungsten is used as filaments in bulbs. And we also use tungsten as kinetic energy penetrators in defense. But unfortunately, tungsten being having a very high melting point, 3400 is the melting point. If you want to sinter tungsten powder, you need to sinter at 2800 degrees centigrade. Whereas we have made nano tungsten by simply taking the tungsten powder that is commercially available, ball mill it for about just 3 hours. Okay, you get a nano tungsten, and that nano tungsten can give you close to 100% density at 1600 degrees centigrade. You are able to save a lot of energy by sintering at low temperatures. Similarly, you can also recover metals from ores by making them nano. For example, we went to Orissa, Sukinda mines, took chromite ore. And typically, chromite ore, when you recover chromium metal out of chromite ore, the recovery is less than 10%. We just ball milled for about 3 hours. And then you see the recovery goes to 90 to 95%. And all this happens because a large surface area is created when you convert something into nano, and immediately it gives you very high reaction rates. We can also make functional materials. This is a copper. Somebody from Crompton, Greece asked us, okay, do you have a way by which I can make copper very strong? Because copper, they use it as a good conductor, but copper is very soft. We said we can make copper into nano and then make it very strong. At the same time, to ensure this nano copper remains as a nano copper, after sintering, we add some amount of tungsten, tantalum, things like that. And when you add them, they go to the grain boundaries and pin the grain boundaries of this copper so that the material retains its nanostructure even after sintering. The grain size is 30 nanometers. Please note that they have all been sintered, completely 100% sintered pellets these are. And you still retain such a small grain size. And that gives you 3 times the strength of what is called a normal oxygen-free high conductivity copper. And these are all possible. And we can also demonstrate that these alloys, we call them as nano composites, they can be sintered at a much lower temperature when compared to a normal material. A micro composite of copper needs about 800, 900 degrees centigrade to sinter. Here at 500 degrees itself, you can sinter. We can also make composites, nano composites with intermetallic compounds and oxides as a combination. We know that intermetallics are very brittle, and also we also know that oxides are also brittle. But when you make a nano composite out of them, you see that the strength is very high, 2500 megapascal, and then gives you almost 13 to 14% elongation, which tells you, I mean, usually these materials are brittle. Their percentage elongation is less than 1% typically, and you are able to produce wonderful combinations of strength to ductility by this kind of combinations. We also did one work with IGCAR Kalpakam, where we try to make what are called fast breeder reactor materials, what are called ODS steels, okay, which are called oxide dispersion strengthened steels, which are nothing but nuclear fuel pins, tubes like this. This is all made out of powders. Okay, we made these ODS steel powders, and now taking the help of IIT Hyderabad, DMRL, and then NFC, they were able to make a 4-meter long tube with a diameter of around 6 millimeters. By simply hipping it and then pilgering and then extruding, people are able to make this kind of tubes. And these are all now available, and such materials give you extremely high strength even at 700 degrees centigrade, which a normal steel such as 9 chrome 1 moly steel gives you strength only up to about 500 degrees centigrade, not beyond 500 degrees centigrade. So we can demonstrate that this is possible. We also developed at IIT Madras a way by which you can see these materials at a very small scale. So this is called National Facility for Atom Probe Tomography, which is called NFAPT, where we got about 2 crores from a number of institutions each. And then with that, and then support of DST, with about 40 crores, this facility has been set up. This is called an atom probe, where here, this is one such image, where each pink dot that you see is an atom of iron. So this is a steel sample with some nanoparticles of yttria inside. All these green particles that you see, they are all yttria nanoparticles, Y2O3. And they are all of 2 nanometer in size or so. And we can actually find out what is the stoichiometry of the particle. We run this particular facility on a 24/7 basis. We actually have 3 operators who run it in 3 shifts. And people send the samples to us, and this is a remotely operable machine. All these partners have a workstation, something like a computer like this here, and they send us the sample. we polish the sample, put it in the microscope, and they operate the microscope sitting in IIT Bombay, IIT Delhi, IIT Kharagpur, Kanpur, IIT Ropar, and so on. Okay, that's the beauty, and this is the first such remotely operable atom probe in the whole world. Okay, and this is something which we are able to demonstrate, and quite a number of people are using it and getting exceedingly good understanding of the materials. For example, this is one such ODS steel where you can see iron, tungsten, chromium, all of them are uniformly distributed inside the sample, but yttrium and titanium and oxygen are segregated into that particle. So it is Y2Ti2O7 kind of a particle. We have been able to prove from the composition of those individual particles. So you can do composition analysis at a very nano scale. No SEM EDS can do this. Okay, and it is possible to do with such atom probe. You can even see what kind of atoms are sitting at the grain boundary. And this is one such example where you can see some elements such as sodium, potassium are going to the grain boundary. You can detect them very easily. And the grain boundary thickness is of the order of 1 to 2 nanometers. And it is possible to see what elements are settled there and what is the composition of that grain boundary. And last few minutes, I want to say a new type of materials which have been exciting many people nowadays are what are called high entropy alloys. 2004, the first paper came out, and ever since everybody is excited about this, which are basically alloys, which are multi-component alloys, which have equal proportion of elements, and that causes the entropy, configuration entropy to be very high. And such a material, when you make it in the form of an alloy, there is a tendency that it forms a solid solution instead of forming intermetallic compounds. Because the entropy being very high, the material would like to be in a disordered state rather than in an ordered state. And that's how we say, for example, you take a 6-component alloy, aluminum, iron, titanium, chromium, zinc, copper. Okay, you can ask me, how did you choose these elements? There are some methodologies by which we choose these elements. When you do that, put these 6 elements in equal proportions into a ball mill it for some time. You simply get that all the individual peaks vanish, and you get a simple BCC crystal structure. And you take these particles, they are all nanoparticles, and put the electron beam on each of the particle. You can get the composition of the particle, and the composition of the particle is very close to what is called equiatomic composition. If you have 6 elements equal in proportion, each element should be 16.6, 100 divided by 6, and you can see this composition very close to that. Within 1 or 2%, 1% or so, it is very close to that. So it is possible to say very uniformly distributed elements in all these nanoparticles. And people have been using atom probes to see whether they are uniformly distributed or not. So here is an example. We made a 5-component alloy, put it into an atom probe. You can see every element is uniformly distributed. You can also see nitrogen, carbon, oxygen. You can even see hydrogen in a material. Okay, which has not been easy by any other spectroscopy technique. Atom probe can do that. We can also see if it is a 2-phase material, how the elements are distributed. Okay, so here is a case where you can draw a line, vertical line from bottom to top, and then see what is called compositional profile. How is the compositional profile in this material? Please note that this whole from top to bottom, this is all about 100 nanometers. So within 100 nanometers, I am able to see how the elements are distributed. All this is possible. And some of these alloys have exceedingly good properties. For example, we found out that this material has very good oxidation resistance when compared to nickel-based superalloys. Okay, this has been patented now, and people are excited. Boeing is excited about it, and and even GE is excited about it. They are trying to develop a newer superalloys with this kind of materials. And the last part I wanted to tell you is not only you can talk about strength of materials being improved by making something nano, you can also demonstrate that their functional properties can be significantly improved. This is one such material, piezoelectric material, PZT. We make it nano, and suddenly you see that this material has a very high dielectric constant, 35,000. A normal PZT has 2,000 dielectric constant, and this can be used for what is called energy harvesting. For example, now this has been demonstrated to ARDE Pune, and ARDE Pune has set up a very big piezoelectric lab, where they are producing these in kilogram levels and then using. For example, if you can make this in the form of a 1 rupee coin, put it into your shoe and keep on walking, can generate every step of yours. Piezoelectric material, when it is compressed, it generates electricity. And a nano piezoelectric material is more sensitive for this. So you can actually generate electricity, okay, and which we call it as energy harvesting. A lot of interesting things can be done. And I think because of the paucity of time, I will stop here. And if you have some questions, feel free to ask.
Yeah, thank you, Professor Murty, for a nice
Thank you. Thank you
presentation,
very much.
which includes the history of materials and then nanomaterials, high entropy alloys. I request if you can take a couple of quick
Sure, sure.
questions. As
10 minutes up to 25, we can go.
Okay. So if there is any queries.
No questions? No questions means everything is understood.
No, definitely.
So we always say, when there is no question, it means you have not understood anything or you have understood everything. Yes, somebody?
Yes, KP Singh.
Yes, sir. Yes, sir.
Yeah, please.
I have one question actually regarding this tomography. Also, is there any charges?
Is there any
Charges?
charges?
Yeah.
Yes, sir. There are some charges. I do agree. What we can do is, national labs, there are very minimal charges. But if you can come through, for you, the closest is Bombay. If you come through IIT Bombay, we do it freely for IIT Bombay, because IIT Bombay has given 2 crores for us. So we call them as partners. Okay. So if your sample comes through IIT Bombay, then we'll treat it as free. Otherwise, there is a certain charge for that. Okay.
Okay.
Because to maintain this facility, you need a lot of money. I can tell you the AMC of it comes to close to 1 crore. Okay. So obviously, I raise money. What I have done is, when I bought this machine, 2018, we have installed this 3 years back, coming to close to 4 years now. We got an AMC for 5 years. Okay. So first 5 years, I don't need to bother. But then after that, I have to pay money. So we are trying our best. In fact, so many people from abroad also use this. We have people from Europe coming, because in Europe, if you want to use the same atom probe, they charge more or less close to about 1,000 euro per sample. Okay. Whereas at IIT Madras, the charges are much smaller. So as a result, people believe this is much better way. And they don't need to come at all. They simply send a sample by post, and we put the sample inside, and we do the sample, and then we send the data to them.
Yeah, that is beauty actually. Yeah, definitely.
So we can do that for you also. We can send the data to you. So in such a format that you can simply put it into your paper or into a report. We can do that.
Okay.
In fact, in the last 3 years, almost 50 papers have been published by the whole country. People from various IITs have used it. Yes.
Thank you, sir. Thank you.
Thank you, Dr. KP Singh. Few more questions we can take. I can see. I have. Yeah, there is one question in the chat box. I'll read out, sir. Could you use atom probe to identify hydrogen in grain boundaries? Also, any requirement of specific specimen preparation?
Yeah, in principle, it is possible. But hydrogen, I would say, is a very recent phenomenon. Last 1 year only, people are trying to do that, because hydrogen is atomic number 1. So it's a very slow diffusing species, actually. I mean, atom probe, if you know the principle of atom probe, what we do is we make the sample in the form of a sharp tip and create a field in front of it. Okay, so that the field, if it is higher than the bond energy, an atom is pulled out. And this atom, once it comes out, the ion, it gets ionized, it comes and hits a detector. And there is a certain distance between the tip and the detector. And this is what is called time of flight measurements. Simply mass spectroscopy. If you are physicists sitting here, you might know mass spectroscopy. This is similar to mass spectroscopy. But the moment the atom comes and hits the detector, I can understand what time it has taken to hit the detector. From the time it has taken, I can calculate back what is the mass of this particular atom. Okay, because the time it takes is a function of the mass, and then the position where it hits tells me the xy coordinates of that particular atom. So when you have atoms in the form of a sharp tip, the first layer is removed, sputtered away kind of, and then that layer of atoms go and hit the detector. Then the second layer, then the third layer. So they keep on going and hitting the detector, and in the software, I again reassemble all this and then create the whole structure once again. So in the process, if you want to have hydrogen being an atomic number 1, it takes a longer time for hydrogen to reach the detector. Okay, so it needs some some kind of a precautions, and people have been doing it. Okay, so you can actually, for example, hydrogen embrittlement we all talk about. Nobody knows how hydrogen embrittlement happens. Okay, so whether it is hydrogen is sitting at the grain boundary and doing something, nobody is able to see it now. But now with this, it is possible. If you go to Scopus or somewhere and put atom probe tomography and hydrogen, you will find a few papers that have come in the last 2 years where people have been able to see hydrogen. Yes? Shall we stop now?
Yeah. No. Maya, she is involved in this tungsten material.
Yeah.
And she has some unique problem of carbon and helium in tungsten. So
Yeah, please, my request to you is go to Google and put NFAPT. It will take you to our website. Just basically, what you have to do is simply there is a proposal. We want you to fill up that proposal. What we want is, we don't want everybody to unnecessarily use it. Nowadays, people say, just come to TM and say, can you please take some pictures for me? Okay, it is not taking pictures like that. So there has to be a purpose for doing that. So we ask you a question: why do you want to use an atom probe? Is there a problem that cannot be solved by a CMR TEM, for example? Okay, once you define that yes, it is there is a problem which only atom probe possibly can solve, then we immediately take it up and then give you a slot, and it can be done. Then you can send the sample. So you can fill up that particular form and send it to me, and then we can take it up.
Okay, Maya, now you have got the reply. And there is one more question from Shitish Acharya.
Yes, max phase materials.
Is like to know your thought about the max phase material and its future in various sectors.
Yeah, max phase is interesting, challenging. Only thing is making, you see, any of these things, the issue is making it in large quantities. Okay, so once you start making it large quantities, or use it as a coating material for certain applications, then it becomes catches up. For example, same problem which we are finding with high entropy alloys also. Now we are trying to make high entropy alloy in the form of powders by atomization. Okay, we are developing a first gas atomizer in the country. I have a project now with somebody in Hyderabad where a first gas atomizer in the country is being developed. We do not have a gas atomizer in the whole country so far. No, people have only imported gas atomizers. You need powders for all this, So if you want powders for even additive manufacturing, we can make these powders through gas atomizer. So max phases can also be thought in that fashion, that we can use it for various either bulk applications or what is called coating applications, and that would be interesting.
And last question, sir. There is one more.
Yes.
Is it possible to give some light on the native oxide layer in aluminium?
Yeah, one can do that. I will tell you a very interesting example. I do not know. This is Uday. Uday, are you a metallurgist by any chance? I see MM. MM means metallurgy, right?
Yes, sir.
Okay, very good. So in a metallurgy, we know, for example, if you have a cast iron, okay, you add a small amount of cerium, okay, and the gray cast iron gets converted into magnesium, and cerium gets converted into a spherical particles, right? Similarly, in an aluminum silicon alloy, you add a small amount of sodium or strontium, the silicon needles immediately become like a spherical particles. The amount that you add is 0.02%, very small. and nobody knew what happens to this. In a nickel-based superalloy, when people made Ni3Al single crystals, they found that they are all brittle. When they added 30 ppm of boron, suddenly this material started becoming tough. And such kind of extremely small percentages when you add, what does this element do? Where does it go? Nobody knew. And we were able to detect all this using atom probe, because it forms a monolayer on the surface. For example, you are talking of alumina. So one can possibly prepare a sample of that and see that top layer of aluminum oxide. In interior, it has an aluminum, let us say. What will be the stoichiometry? Please understand that one machine cannot give you all information. For example, atom probe cannot tell you the structure of that alumina. Whether it is alpha alumina, beta alumina, it does not tell you. But it tells you what is the stoichiometry of it. All these can be found out. So you have to always, nowadays people call it as correlative microscopy. I combine TEM understanding, SEM understanding, optical microscopy understanding, AFM understanding, and atom probe understanding, and get an overall picture of the material. There cannot be, I mean, if I have two different health problems, same medicine I cannot use, right? So you cannot have one answer for all questions in the world. So atom probe is very good for giving you what is called compositional analysis at the nanoscale, which a normal TEM or any other microscope cannot do. That too in 3D, not in 2D, and that's the beauty of it. Okay. So with that, I think we'll stop. Thank you very much, Paritosh.
Okay. Thank you, sir. We have many questions, but definitely.
No, but we will have some other time.
We can contact you later with all these
Thank
queries.
you.
Thank you
very
for
much.
thank you for your such an informative talk. Thank you once again, and let's give him a big hand.
All the best to all of you, friends.
Thank you.
Bye. Bye.
Thank you.